Hey, it is physics time. Woohoo! Today we are talking about oscillations. In particular, a certain sort of oscillation that we call simple harmonic motion. I'm going to set this thing going. I am not attempting to hypnotize you. I doubt that it would work. But this is an oscillation. Now let's talk about what we can, this oscillation's going slightly the wrong direction. I'm going to start it again. It's not cooperating. That's better. Here's our oscillation. Now this is oscillating backwards and forwards, again in slightly the wrong direction. Doesn't matter too much. What do we notice here? There are some certain things we can observe about oscillations. It's a repeated motion. It's a repeated motion. It passes through what we call the equilibrium position. That's the position in the middle that it always kind of wants to end up at. So when you think about it, this thing is accelerating down this way, then it's slowing down, and it's accelerating, and it's slowing down. It's always trying to get to this point. That's the equilibrium position. Straight up and down, vertical. Alright? Equilibrium position. What's the amplitude? Amplitude is the maximum distance away from equilibrium. If here's our equilibrium position, amplitude is out there somewhere. I just messed it up. That's the amplitude. On the other side, that's the amplitude also, but it's in the negative direction. Okay, we've got equilibrium position, we've got amplitude, negative amplitude. We've also got displacement. Now, displacement, you know, it's kind of like distance. Well, displacement is at any point in time, it's how far this thing is from equilibrium. So let's say right now, it's maybe, I don't know, 3 centimeters from equilibrium. If we left it a fraction longer, it would be out further. Then it would get to A, maximum amplitude, then it would start heading back. The displacement is continually changing. But the amplitude is the maximum distance on either side from the equilibrium position. Okay, all good so far? We've got equilibrium, amplitude, and displacement. We've also got, try and hypnotize you again, we've got the period. Now the period of motion, you probably know this, is the time taken to complete one cycle. So if you've got your stopwatch, you're going click, click, and it might be 1.1 seconds or 0.85 seconds. That's the time taken, technically it's the time taken to get from equilibrium through a whole cycle and back to equilibrium again. I have no idea what the period of this is, but let's just say it's 0.5 seconds. It takes 0.5 seconds to get from here through complete motion back to there again. One period. Let's say it takes 0.5 seconds. That's the time taken to complete that motion. What would the frequency be? Frequency is number of cycles per second. It's the inverse of the period. Frequency is 1 over period. So if the period was 0.5 seconds, what would the frequency be? That's right, it would be 2 cycles per second, because you'd get 2 of them happening in 1 second. So period, time taken for one oscillation, frequency, number of oscillations per second. Now, things get a little bit confusing at this point. There's this term angular frequency. You remember back to when you did circular motion? Angular frequency was, well, a period was the time to go in a complete circle. Angular frequency was the number of radians you'd turn around a circle in a second. Number of radians. Now, how many radians are there in a complete circle? There's 2 pi radians in a complete circle. So we think of it like this. The angular frequency, or the angular velocity in a circle, something moving in a circle, would be the number, the distance travelled, or the angle turned through, which would be 2 pi to get right round in a circle, divided by the time to get right round, which is a period. So it would be 2 pi divided by period, 2 pi over t. Now, remember, this is not moving in a circle. So why on earth are we talking about circular motion? Well, I'll get to that in a minute. There is a good reason. But let's just imagine if this was a circle, then the time taken to get from starting point back to here, back to there again, think of that as one revolution. If that's one revolution, then the angular velocity, or the angular frequency we call it, would be 2 pi radians divided by the time, or the period. So omega, angular velocity or angular frequency, equals 2 pi radians divided by the period. Now, back to what we said before about frequency. Frequency is 1 over period. So if you have omega equals 2 pi over t, a little bit of simple maths soon shows you that omega equals 2 pi times frequency. A little bit confusing? Yeah, just a bit, but you'll get there. It's leading somewhere. Finally, I want to talk to you about phase difference. Phase difference is when two things are moving in simple harmonic motion, but they're out of phase. So if I go like this, now I know you think that this is a really cool dance move. Good on you. Those are in phase. But if I go like this, now I'll get myself really confused. No, I'm not confused yet. These are out of phase. In fact, they're about 180 degrees out of phase. When one hand is up, the other hand is down. Back in phase. Everybody together now. Out of phase. Okay, that's phase difference. Right. Now we're going to try something. There are 3 key facts. Get rid of this. 3 key facts that I want us to understand, and we need to understand about simple harmonic motion. Now, if this works, I'll be really, really pleased. If it doesn't work, well, it's worth a try. Here we have a sinker on a string, which really in physics is a pendulum. Who cares about fishing? It's all about demonstrating physics. Here we have a drill with something stuck on the end of it that is going to move in circular motion at a constant speed. I hope. Now, I'm going to keep the centre of the drill at the equilibrium position of this pendulum. It's not a sinker, it's a pendulum. And I'm going to see if I can show you what happens when we watch this little black dot and we watch the sinker, if I can get them in phase together. Remember in phase? The dance move? Right? In phase. So let's see if we can get them in phase. This could be tricky. So, get that spinning first. Okay. Okay, yep, it's tricky like I thought it would be. When you look at the dot, oh, that had to happen. So, it was just starting to work well. And then the two collided. We won't give up. Drill needs to be moving at a constant velocity. If you watch this carefully, you'll notice if you look at the black dot and the sinker, they're kind of in line with each other. I hope. There's a reason for that. And I'll stop now before we get too out of phase. We're not going to stop the clip, but what's going on here? Well, I'll let you in on a little secret. There is a relationship between circular motion and oscillation motion, or simple harmonic motion. They actually, if I try and do this, I'll really mess it up. But if you look at the horizontal dimension only of circular motion, you'll notice that that little black dot was moving exactly in sync with this sinker. And if it wasn't, it's because it's really hard to make one of these drills move at a constant velocity. Normally you use a turntable that moves at a constant speed, but we're in lockdown and I'm stuck at home and we don't have a turntable, and so I'm using this, and you know, it's actually quite fun. I'm having a good time. What does all this teach us? Well, hopefully it teaches us something. The point is, when an object is moving in simple harmonic motion, the simple harmonic motion is exactly the same as one dimension of circular motion. One dimension. You're looking at the black dot and it's staying. If you just look at its horizontal motion, it's matching this guy. They're staying the same. So if you look at one dimension of circular motion, it's the same as simple harmonic motion, which means we can pull out all that trigonometry that we've done in maths, because you know maths is a meaningless, pointless subject unless you apply it to physics, right? So I need my pen. So if we have here something oscillating on a spring, that is a spring, and this object is oscillating backwards, up and down, up and down, up and down. At the moment it's on its way up. It's heading upwards at the moment. Now it's heading up, and we could trace its motion in a little graph. If this was time and this is displacement, well, it starts at equilibrium position. That's equilibrium position there, that dotted line, and it moves up to its maximum amplitude, maximum displacement at amplitude A, back down through equilibrium, down to maximum displacement at the negative amplitude, back through equilibrium, and it just keeps going and going. It's bobbing up and down on a spring. We could have used this, but we're using a spring instead. Same thing, same idea. So here it is, it's on its way moving up. Now we can think to ourselves, if this can be related to circular motion, then all you have to do is draw a circle. Now, I won't draw a very good circle because, well, I don't have much space and I'm actually pretty bad at drawing circles. But here's a circle. There's the middle of the circle. We could draw a triangle here. Here's our displacement here. It's that distance there. X displacement. Here's